Good afternoon, ladies and gentlemen, and fellow engineers. I'm Jimmy of Electrical and Mechanical Services Department of Hong Kong Government SAR. My work is more related to the maintenance contract administrations, and safety and maintenance quality is our prime concern. Today, me and our working partners one of the author, Scotty, we're going to present with you what's of our paper that we present to you on what we do using the new technology to provide different views on conventional problems. As this is an initial project, we have deployed various of IoT sensors to collect data on temperature, strain, acceleration, displacements of lifts. And for this data collected, we'll perform the data analysis for some, we will check if this is a malfunction of the lift. Our goal to achieve real-time monitoring and return its corrective maintenance into proactive maintenance or even predictive maintenance. As you see on the picture there, this is sensors we use and which part of the lift component we have deployed. It's like on the car body, in the car floor leveling accuracy, and on the door lock, we detect the door closing and opening the positions. On the ropes, on the track motor, see the vibration and temperature, and the brake arms. On the current, and we have the wireless connection to the lift car inside the lift shaft, inside the lift machine rooms. And this is our initial trial project. So you see, which we have only deployed for elevators here. It's not that many, but we still have some interesting findings we can share with you today. Okay. Shall I pass it to Scott? Yes. Thank you.
You guys hear me okay? Okay, yeah. So thank you, Jimmy. So I'm going to talk about a few findings that we think may be useful to share. So finding number one, so it's about lift car shaking. So by shaking, we mean that there's a vibration in the lift car, and then the passenger kind of feel it. But it's quite objective, right? Sometimes you feel it's vibrating, and then it's kind of okay. But then oftentimes it's not being reported or not recorded. So and I think only when there's a very severe vibration, then the passenger will report it to the facility owner, and it's get logged into our logbook. So in this study, we're trying to use a more subjective approach. So we use an industrial standard in Hong Kong that it somehow suggests that acceptable vibration is somewhere around 0.25 meter per second square. So we use this criteria, we scan through the vibration data that we collect in 1 year across the 4 elevators. And then we pick out all the journeys that has a peak-to-peak vibration higher than this threshold. And then we classify those travels as lift car shaking. So then we plot the number of lift car shakings happen in our study. So here's an example of 2 of the elevator. The elevator number 1 is the relatively problematic one. We find that there are 500 lift car shaking events during the year. And then the relatively normal elevator 2, we find that only a few shaking happen during the year. So we think that this kind of a matrix may be a good measure, a good way to quantify how shaky is your lift car. And then apart from counting it, we also analyze the frequency spectrogram. So because it's a vibration, obviously we look at frequency, right? So elevator number 1, the problematic one, we see that in the spectrogram, we cannot see a very distinct frequency band. Instead, you see a dispersed frequency. It's probably because there are vibration from different frequencies, so there are no distinctive pattern. But then in a relatively normal elevator, number 4, we see a distinctive frequency band in the frequency spectrogram. So I think this is another way we can use to quantify how the lift car vibrate and how much it vibrate. So we move on to the second findings. The second findings is about the brake arm engagement. So I think by common sense, we think that like how a brake arm operate. Basically, when the car moves, the brake arm should disengage, and when the car arrives at a designated floor, the brake arm should engage, and then the lift door start opening, right? And that's the two columns, the two journeys that we quote here. So the first, the top graph is the motor current, which show what time the lift car travels, and this second row is the brake arm activity, the strine of the brake arm, and the fourth one is the lift door gap. So you see that actually in the Patua region is where the lift car is traveling, and then at the end is where the lift car arrives and the door open. So we found that actually the brake arm not only engage or disengage once, but it actually engage and disengage multiple times when it starts to open the door. So it's kind of unexpected activity that we found. And using this criteria, actually we count, the number of occurrences. There are quite a lot. There are 20,000 incidents that this pattern happened. So I think we haven't figured out why, but I think it's still to be investigated by the lift operator. That's kind of unexpected. And we have type 2 brake arm abnormality that we observe. That's even more strange. So we see that when the car is moving, the brake arm still trying to engage and disengage multiple times when the car is moving, which is quite unexpected. And for this condition, we found out 16 incidents happen in the period of a 1 year study. Yeah. So and then finding number 3, we tried to study the door as well. So it's about the door malfunctioning. So it's pretty straightforward. We have a proximity sensor to measure the distance between the lift doors. So obviously a normal operation, we should see a fully open the door or a fully close the door. But then this is an example of kind of abnormality that we're trying to pinpoint. It starts from completely close the door and then it open completely. But then when I try to close, it actually stuck somewhere in between for, let's say here is around 20 seconds. So this is a kind of abnormal door profile that we're trying to look for. In our study, we use one data science or machine learning way. It's called XGBoost. So basically, we use a sliding window of 100 data points to collect normal and abnormal waveform from the door profile, and then train a classifier to classify whether the waveform is normal or abnormal. And then using this method, we managed to pinpoint actually quite a few abnormal door activity during the year. So some of them happen during maintenance period, which may be normal because maybe the engineer is trying to test it. But it also, let's say in elevator 2, it also happened during the normal hours. So we think that this method actually is maybe a good way for us to quantify how many lift door malfunctioning happening during the year, because obviously you cannot keep looking at the door all day, right? So this is one of the benefits of having a real-time and then continuous monitoring. And so we'll quickly move to the final findings. Number 4 is about the floor leveling performance. So we install a camera on the lift car top, and then we install a visual marker on each floor. So by capturing the image and then compare the image, we can see how much floor leveling deviation each time the lift car arrives at the floor. And then we take that statistic over 1 year's time, and then we come up with a graph like this. So the left-hand side, in the left-hand side, the black curve is actually the deviation of the floor leveling during the year. And we see that one interesting observation is that the green line is actually when we do a regular maintenance. So we notice that after effective regular maintenance, actually the floor leveling deviation reduced significantly. And then on the other hand, if there are no regular maintenance, actually we can see the deviation gradually increase. So and And also the blue color is actually another way to measure it. We use, let's say you can use interquartile range, some kind of statistical method to measure it as well. But anyhow, the concept is that by measuring that, I think this may be a good way that we can quantify any deterioration in the fault leveling performance, and therefore you kind of figure out a way to schedule and arrange your maintenance activity in a more wiser way. Right? So that's the fourth finding. And so it comes to the conclusion. So in this paper, we present a trial of a health monitoring platform for Lift using big data. And then we actually shown that using non-intrusive sensor, we can measure the healthiness of some of the critical components. And then with some statistical method and machine learning method, we can kind of detect the faults and quantify the faults. And then compare that result with our logbook, we're actually able to detect those reported incidents as well as those unreported incidents. So we think that this study is kind of useful, I think, to achieve a conditional-based maintenance strategy, and also we suggest to further validate and try this method in other lift systems. And that brings us to the end of our presentation. And thank you for listening. So welcome any questions.
I would like to mention the pain point of this project. The maintenance qualities, we should give the credit to the lift companies. It's too well. It's very hard to find the fault, so you can see from our PowerPoint there, a few faults can be found. So we need to expand the project to more lifts, so that we can have more data to study. Yes.
Thank you both.
Thank you.
Thank you very